OCaml is an example of an eager programming language. To see what we mean by that, we can look at a few examples. Here's a function that's applied to an argument. When OCaml evaluates this expression, OCaml first evaluates the argument, and then we substitute the resulting value into the body of the function. Note that this is true even if the function never uses the argument. In this case, for example, OCaml will still eagerly evaluate the argument, even though it's not necessary, because the argument never gets used. The same is true for let expressions. When we let a variable equal some expression in some other expression, OCaml will eagerly evaluate the definition expression as soon as it's encountered, even if that expression is never needed later. And that's one of the downsides of this eager approach to evaluation. By evaluating values as soon as they're encountered, we might be wasting effort if we end up evaluating an expression that ends up not needing to be evaluated. That's not so much of a problem in these cases where the evaluation is relatively inexpensive, but imagine that we instead had some function that was costly to evaluate. We'd be spending a lot of resources unnecessarily. This is especially apparent if the function never terminates. Here's a function forever that repeatedly calls itself recursively and never terminates. If we let some variable be the result of evaluating that function, this evaluation will never terminate, even though the variable doesn't get used. An alternative approach would be what's known as lazy evaluation, where rather than evaluate expressions as soon as we encounter them, we delay computation until that expression is needed, and only then is the computation forced to occur. There are some constructs in OCaml that do behave lazily. One is the conditional expression. In a conditional expression, we have an expression that follows the then and an expression that follows the else. Neither of those is evaluated initially until the test condition is evaluated to true or false, and then we only evaluate one of the two branches and not the other. So if we had a conditional expression where one of the branches never terminates, as by calling the forever function in this case, as long as the conditional chooses the other branch, the expression will still terminate just fine. We never evaluated the forever function, it's delayed until it needed to be evaluated. Another example of an OCaml construct that behaves lazily is the function itself. If we had a function whose body was a call to this function forever, notice that a computation that just evaluates to that function does terminate. The body of the function doesn't get evaluated until the function is applied, and in this case, we haven't applied the function yet. Notice then that this gives us an approach we can use to delay computations. If we have some expression, normally that expression would just get evaluated immediately. But if we want to postpone the evaluation of the expression, all we need to do is wrap the computation inside of a function, essentially delaying the computation until we force the computation to evaluate by applying the function. The input to this function is just unit in this case. We don't need the input to the function to have any meaningful value, since the only purpose of using a function here is to delay the computation. So unit makes sense as a value that isn't representing any meaningful information. So what can we achieve with this ability to delay computation? One interesting application is the ability to create infinite data structures. Infinite data structures seem counterintuitive, as it would seem like it shouldn't be possible for us to represent an infinite data structure in a computer with finite resources. But by taking advantage of lazy evaluation and delaying computation until it's needed, it's possible. We'll take a look at the example of a stream, which you can think of like an infinite list. Recall that we could build our own type for a list by giving it two value constructors, nil for the empty list, and cons for combining one element with a remaining list. An alpha stream we might try to define similarly, but in this case it will only have one value constructor, cons, which accepts an element of type alpha, and another alpha stream. Note that there's no nil case here. There's no point at which the stream ends. Every element is consed onto another infinite stream. We could define functions to work with streams, much like we could with any other type. Here, for example, is a function that takes a stream and returns the head of the stream. We're pattern matching directly in the function argument since there's only one value constructor that can be used for streams, and then we return the head. We could similarly define a function to return the tail of a stream too. A challenge comes when we need to try to define a stream value. Let's say, for example, we wanted to define a value s of type intStream. We'd use the value constructor cons, followed by an integer, say the number 1. But then we'd need to provide an int stream as the stream that follows it. Since we're defining s to be of type intStream, we could try to use s here as the stream. But this is a problem. OCaml will give us an error because we're using a name that's unbound. We can't use the name s inside the definition of s. That said, we do have a way that we can use a name inside of its own definition, and that's with the letRec construct. By using letRec here instead of let, we can define this stream, a stream whose head is the number 1 and whose tail is itself, another stream whose head is 1 and whose tail is itself again. What we've created here is an infinite stream of ones, so this stream is perhaps more appropriately named ones. And OCaml's interpreter shows us that we have an int stream that starts with 1 and then cycles. OCaml realizes that the data structure is referring back to itself. And now we can give our stream-related functions a try. Taking the head of the stream gives us back the value 1. Taking the tail of the stream gives us another stream. And taking the head of the tail of the stream gives us another value 1. Of course, taking the head and tail of an infinite stream of ones isn't all that interesting or useful, so let's try to do more with these streams. Since they're constructed similarly to lists, we might try to define other list-like operations on streams. For example, we have the map function for working with lists, so let's try defining a function smap for mapping over a stream. The goal will be to have smap accept a function from alpha to beta and an alpha stream. We'll want to apply the function to every element in the stream and return a new beta stream. How do we construct that stream? We'll use the value constructor cons. The first element of the new stream is the result of taking the first element of the original stream and applying the function to it. So we'll apply the function f to the head of the stream. And what comes next? Well, we can recursively call smap, mapping the function f over all of the elements in the tail of s. We now have a function that maps over all of the elements in a stream. So let's try to use it. We have our infinite stream of ones. If we wanted, say, an infinite stream of twos, we could try to map the successor function over the stream of ones. We would hope that this would give us back a stream with all of the ones incremented, giving us an infinite stream of twos. But that's not what happens. Instead, we get a Stack Overflow error. What's going on here? Well, we're trying to perform an infinite number of computations. We apply the successor function to the first element in the stream, then make a recursive call to apply the successor function to the second element in the stream, then make a recursive call again, and so on infinitely until we run out of space in the stack. In other words, we're trying to perform all of these infinite computations eagerly, which isn't going to work. Instead, we want to delay all of these computations until they're needed. We want them evaluated lazily. We've already seen that wrapping computation in a function is a way we can delay computation. So let's rewrite our definition of streams to wrap the stream inside of a function. We'll define a new auxiliary type, alpha stream internal, to represent the data stored inside of a stream, the cons of some value of type alpha, and an alpha stream. And then our alpha stream will be a function from unit to alpha stream internal. In other words, we're taking a stream internal and delaying its computation by wrapping it inside of a function. So with this new type for streams, how could we define our infinite stream of ones again? A stream can't be constructed immediately with a cons value constructor anymore. Instead, a stream is a function whose argument is unit. In the body of the function, we'll need a stream internal. And according to our definition, a stream internal is the cons of a value like 1, and a stream, like ones. Our functions for working with streams need to change now too. We can't just match a stream directly against the cons value constructor, because that's not what a stream is anymore. Instead, a stream is a function, and when we apply the function with the unit argument, we get back a value that we can pattern match against cons. So to rewrite our head function, instead of pattern matching s directly, we first call s, applying it to unit. The function returns the cons of a head and a tail, and we can return the head. And similarly, for the tail function, we can do the same thing but return the tail instead. And now we can try to redefine our smap function. Remember that before, we could define our smap function, but anytime we tried to use it, we'd run into a Stack Overflow, because we'd be eagerly evaluating the result of mapping over an infinite stream of values. This time, we've defined a stream to be a function. So if we're mapping f over a stream s, the output is going to be a new stream. In other words, a function whose argument is unit. And only when that function is applied will we evaluate the cons of applying f to the head of the stream, and then recursively calling smap of f on the tail of the stream. Because we've wrapped that recursive call inside a function, we've delayed that recursive call. It's not going to happen eagerly, it's only going to happen when we apply the function and force it to be evaluated. This means we can define our stream 2's to be the result of mapping the successor function over 1's. And this time, the computation terminates, and we get a value. We've gotten ourselves an infinite stream of 2's. How do we know that this is really a stream of 2's? We could check some of the elements one by one. Take the head of the stream and see that it's 2, take the head of the tail of the stream and see that it's 2, so on and so forth. But we can define some functions to make this easier for us. Let's define a function first that takes an integer n and a stream s. It will return a list of the first n elements of the stream s. So if n is 0, there's no elements to return, and we'll just return the empty list. Otherwise, we'll return the head of the stream, followed by the first n-1 elements of the tail of the stream. Using the first function, we might compute the first 5 values in the 2's stream, and see that we get back a list of 5 2's. But working with infinite streams isn't particularly useful if all of the values in the stream are always the same value. So let's see if we can instead define an infinite stream of the natural numbers, starting from 0, then 1, then 2, then 3, etc. How would we define a stream to be this infinite sequence of natural numbers? The sequence starts with a 0, that much we know, but we can't possibly list out the entire infinite number of remaining values, so how else could we characterize the rest of this stream? Well, you might notice that the rest of this stream is just the natural numbers, with each value increased by 1. In other words, instead of starting 0, 1, 2, 3, it starts 1, 2, 3, 4. So we can define the sequence of natural numbers recursively. We start with a 0, and then we have the sequence of natural numbers with 1 added to each of them. We can write that definition like this. We'll recursively define a stream nats for the natural numbers. It's a stream, so it's a function whose argument is unit, and evaluates to cons of 0, and the result of mapping the successor function over itself, a stream of natural numbers. And just like that, we've represented an infinite stream of natural numbers. If we want to see some of them, we just need to force them to evaluate. We could take the first 5, for example, and see that we do get back the first 5 natural numbers. The possibilities get even more interesting when we can combine multiple streams into a single new stream. For example, we could define a function smap2. Smap2 will be very similar to smap, but instead of applying a function to each element of one stream to get the elements of a new stream, we'll instead apply a function to each element of 2 different streams, combining those elements to get the elements of a new stream. So the output is a stream that, when applied, will give us the cons of the function f applied to the head of both streams, and then recursively calling smap2 of f on the tails of both streams. Why might we want to combine multiple streams into one? Well, let's try to define a stream to represent the Fibonacci numbers, an infinite sequence of numbers that starts with 0 and 1, but after that, each element is the sum of the previous two. We know that it starts with 0 and 1, but how can we recursively describe the rest of the stream? This 1 is the result of summing together 0 and 1. The 2 here is the result of summing together 1 and 1. The 3 is the result of summing together 1 and 2. The 5 is the result of summing together 2 and 3, and so on. So what you might notice is that this remaining sequence of numbers is just the result of taking the sequence of Fibonacci numbers and adding the tail of the sequence of Fibonacci numbers. In other words, the same sequence but without the 0. This lends itself to a concise definition. We can define the stream of Fibonacci numbers fibs to be a stream that starts with 0, and then a stream that starts with 1, and then the result of using SMAP2 to add together the Fibonacci numbers and the tail of the Fibonacci numbers. The result is an infinite stream of the Fibonacci numbers, and we can generate the first few values of the sequence to show that. One thing you might notice, though, is that when we try to generate more Fibonacci numbers, the process is quite slow. It takes a few seconds to generate. What's taking so long? Well, there's a lot of repeated calculation going on here. Getting the 10th Fibonacci number, for example, requires summing together the 8th and 9th Fibonacci numbers, which requires summing together the 6th and 7th, as well as the 7th and 8th Fibonacci numbers, and so forth. You'll notice that many of these values will end up getting computed many times. But there's no real reason to compute the same number multiple times. When we're working in the pure part of the language with no side effects, computing the same expression will always give us the same value. Rather than recalculate it every time, we'd be better off remembering the value we calculated the first time, and then just reusing that value later instead of recomputing it. This process of remembering a value to avoid needing to recompute it in the future is called memoization. If we wanted to implement that idea for ourselves, we could do so. We'll define a new type, alpha thunk. A thunk is going to represent a value that might initially not be computed yet. Once it is computed, though, we'll remember the value so that we don't need to recompute it again in the future. In order to do that, we need some way to update what's stored inside the thunk once we've computed the value. That means we need mutability, so we'll define our alpha thunk to be a reference to an alpha thunk internal, where a thunk internal can exist in one of two states. It might be unevaluated, in which case it's going to store some function that will compute a value of type alpha, or we might have evaluated it, at which point it's just going to store that value alpha. How do we access the value inside of a thunk? We'll do so via a new function that we'll define called force. What force will do is it will take a thunk, and if it's already been evaluated to some value v, it just returns that value v. Otherwise, if it's unevaluated, we're going to call the function to evaluate it, and then store that newly evaluated value inside the thunk. And now that the thunk stores an evaluated value, we can call force on it to return that value. So whenever we apply force to a thunk, we get back the value stored in that thunk. But the thunk will only need to evaluate its value once. After it's been forced once, it never needs to recompute its value. It will just return the same value that was already calculated every time it's forced in the future. So with this new data type, we can create thunks anytime we have values we want to compute once and then remember. Here's a function, for example, that first prints a message saying that it's evaluating, and then calculates the factorial of 15. Let's define a new thunk to be a reference to unevaluated and that function. So the thunk represents the factorial of 15, but it hasn't been evaluated yet. If we were to force the thunk to evaluate, we'd see that the function gets called, and it prints the fact that we're calculating the factorial, and we get back the factorial of 15. But if we were to force the thunk to evaluate again, the function doesn't get called again. Nothing's printed because the thunk has already calculated the factorial of 15 once. It was then saved so that it could be reused in the future. This idea of using thunks to delay computation and then save the result of that computation is useful enough that OCaml has some syntax features and an entire module, the lazy module, dedicated to working with lazy computations of this form. Instead of using our own custom alpha thunk type, we can use the built-in alpha lazy.t type. This type represents some delayed computation of a value of type alpha, a computation that will be remembered once it's evaluated so that it can be reused in the future. To create a new lazy value, we can use the lazy keyword, followed by the expression whose computation we want to delay. And if we have a lazy value and want to force it, we can use the function lazy.force. This works essentially the same way our thunks did. If we have some computation, like the factorial of 15 that we want to delay, we'll use the lazy keyword, followed by the expression to compute the factorial of 15. Normally, the factorial of 15 is an int, but since we've wrapped it with the lazy keyword, it's instead a lazy int. If we want to force it to compute, we can call lazy.force on the lazy value, which performs the computation and gives us back the value. And once the value is computed once, it doesn't need to be computed again. If we were to call lazy.force later on the same lazy value, no recomputation happens. We just get back the value that's already been computed. The lazy module then gives us several benefits. We can use lazy values to delay computation until we need it, potentially avoiding computation of values that are never needed, and also allowing us to represent infinite data structures like our infinite streams. You could, for example, re-implement our stream data structure using lazy types instead of with functions. This would give us the added other benefit of the lazy module, memoization, the ability of these values to remember the results of being computed the first time, so that we don't need to waste resources recomputing those same values again in the future.